In this video, we're going to be talking about how to graph a function using all of the tools that we've learned so far in our algebra classes and in calculus so far. So this can kind of test you on everything that we've done in this section so far. It's very inclusive. So all of these are the topics that you want to be familiar with and where to find them in your textbook. Some of these are in the prerequisite chapters, some of them are in chapter 1, chapter 2, and most of it's in chapter 3. So this is a combination of algebra and calculus, and we're going to use everything that we have in our toolbox in order to get the best possible sketch of a function. So basically the steps are this. You want to figure out everything that algebra can tell you, definitely the domain, the range, the intercepts, the asymptotes, any symmetry that you have. We also want to find out what calculus can tell us. So that's going to tell us our relative extrema, where we're increasing or decreasing, our concavity and points of inflection, and that sort of thing. So let's take a look at an example, and we're going to go through this from start to finish. So we want to analyze and sketch a graph of f of x equals x to the fourth minus 6x cubed plus 9x squared. So if I'm looking at domain and range, this is a polynomial, so its domain is going to be all real numbers. We don't have any problem with the domain, okay? But when it comes to the range, that can be a little bit trickier to find, and if you can't find the range right away, that's okay. You'll eventually get there. But one thing that you can do is you can factor this, which will give me x squared minus 6x plus 9, and the x squared minus 6x plus 9 happens to be x minus 3 squared. So you can see that in this case, we've got a squared and a squared, so those are both going to go positive, so this will never be negative. So the range here is actually going to end up being very predictable. It's going to be from 0 to infinity. So this time it's easy to find the range right off the bat. It isn't always. You may also remember a trick where if you look at the degree, which was 4, so it's even, and a sub 4 happens to be 1, which is positive, that means that your end behavior is going to go up on the left and up on the right. So you can use those tricks as well if you remember them from your algebra classes. The next thing I want to do is find the x and y intercepts. So the x-intercepts mean we're going to set y equal to 0. So I'm going to go ahead and use that factored form that I found earlier. Use whichever form is more convenient and set it equal to 0. So that gives me x equals 0 and x minus 3 equals 0, or x equals 3. So I have an x-intercept at 0, 0, and 1 at 3, 0. And again, if you want to throw in some algebra, you can check the multiplicity. The multiplicity of each of these is 2 because it's squared. So we have a multiplicity of 2 for both of these, and you can expect that both of these points, the graph will bounce off of the x-intercept. So you can use any of that you're comfortable with. If not, that's okay. You don't necessarily need it. To find the y-intercept, we want to set x equal to 0. I'm just plugging that in, and I get 0. So we have a y-intercept of 0, 0. If you're interested in the symmetry, there's 2 types of symmetry that you want to check for. You can talk with symmetry, or symmetric with respect to the y-axis. And the test for that is testing if the function is even. So you want to know, is f of negative x equal to f of x? So in this case, f of negative x would be negative x to the fourth minus 6 times negative x cubed minus 9 times negative x squared. So that gives me x to the fourth plus 6x cubed plus 9x squared. Or sorry, minus 9x squared. Actually, ignore me, this was supposed to be a plus right here. So it is plus 9x squared. But either way, this is not equal to f of x. It's not the original function. So there's no symmetry with respect to the y-axis. You also can talk about whether the function is symmetric with respect to the origin. And the test for that is if the function is odd. So you want to know, is f of negative x equal to negative f of x? We already found f of negative x, so let's just find the other one. Negative f of x would be negative x to the fourth plus 6x cubed minus 9x squared, which is not equal to f of negative x. So there's no symmetry here, and in this case there's actually no symmetry in this graph. And that can be just as useful as knowing if there is symmetry, because if your final graph looks like it has some symmetry, you probably did something wrong. All right, vertical and horizontal asymptotes. Again, our function is x to the fourth minus 6x cubed plus 9x squared. There's no denominator here, so there's no vertical asymptote that we have to worry about. If we wanted to check for horizontal asymptotes, we would find the limit as x approaches infinity of f of x, which is going to be the limit as x approaches infinity of that polynomial, which is going to be positive infinity, and the limit as x approaches negative infinity of f of x would be the limit as x approaches negative infinity of that polynomial, which, because we've got our leading term as a fourth, again, that's going to be positive infinity. That a fourth term kind of takes over. So there's actually no horizontal asymptotes here either. This does give us another way to find the end behavior though, so if you don't remember that trick with the degree and the coefficient, you can always just use the horizontal asymptotes test, and that will tell you your end behavior. So that's everything that we can get from algebra and from limits. So from this point forward, we're going to be dealing with the chapter 3 stuff, which is, you know, what we can tell from the first and second derivative. So that's what we want to deal with. So I'm going to find the first derivative, which is f prime of x equals 4x cubed minus 18x squared plus 18x. And that's a polynomial, so it exists everywhere. If I set it equal to 0 and factor, this factors to be 2x times 2x minus 3 times x minus 3. So if I set that equal to 0, I get critical numbers, or critical points of x equals 0, 3 halves, and 3. So I probably could do the second derivative test here, but because I want to know where this thing is increasing or decreasing, I'm just going to go ahead and do the first derivative test, because that'll tell me that information and my relative extrema. So I'm going to set up intervals. So I will have negative infinity to 0, 0 to 3 halves, 3 halves to 3, and 3 to infinity. And I'll pick my test points. So I would have negative 1, 1, 2, and 4. Those are just the ones that I'm choosing. Plug them into f prime of x, and I get negative 40, 4, negative 4, and 40. So my conclusion is that we are decreasing, we are increasing, we are decreasing, and we are increasing. So that means that this point at 0 has to be a relative min, a relative minimum. This one would have to be a relative max, and this one would have to be a relative min. So I'm just going to plug those points into my original function, f of x, and get the y values. So I would have 0, 0, 3 halves. When you plug f of 3 halves, you get 81 over 16. And when you plug 3 in, you get 0. So that's everything that the first derivative can tell me. So let's go ahead and take a look at the second derivative. If I take the second derivative, I get 12x squared minus 36x plus 18. Again, that's a polynomial. That exists everywhere. So if I set it equal to 0, and I solve, I could use the quadratic formula, whichever, or try to complete the square or something like that. I don't think this one factors. I would get 3 plus or minus the square root of 3 over 2. Now, again, this is not a very pretty number. These are our potential points of inflection, but I do want to at least kind of know where they exist. So if I find the positive of this, I get about 2.37, and the negative of this, I get about 0.67. So we're going to check for concavity. So I need intervals. So I'm going to have from negative infinity to 3 minus the square root of 3 over 2, which is that 0.67. From 3 minus the square root of 3 over 2 to 3 plus the square root of 3 over 2, which is the 2.37. And from 3 plus the square root of 3 over 2 to infinity. I'm going to pick my test points. So choose easy ones. Why don't we pick 0 between 0.67 and 2.37 would be 1, and greater than 2.37 we could pick 3. We plug them into f double prime of x, and you get 18, negative 6, and 18. So our concavity here, this one is concave upward because it's positive. This one is concave downward because it's negative. And this one is concave upward because it's positive. So that's my concavity. And then the very last thing is you want to verify that both of these points where it changes from upward to downward or from downward to upward are points of inflection. So we do have an inflection point at 3 minus the square root of 3 over 2, and then I just want to plug in to that y value. Now I'm going to be graphing it. This one's not a very pretty number. We're going to estimate it at about 2.25 since we're going to be graphing it. Normally I wouldn't tell you to do that, but if you are graphing, you do want a decimal approximation. We also have an inflection point on the positive half, 3 plus the square root of 3 over 2, and it also evaluates to about 2.25 with the original function. So we're going to use those for our approximations. Now the reason why these are inflection points is because, remember, the graph is actually defined at both of those points, and it would have a tangent line at both of those points. So the next thing is to put it all together. Now, some people don't need this step, but it really helps me to organize my graph if I put everything on a number line before I try to actually put it on the graph. So I'm going to draw kind of a sketched out number line. It doesn't have to be to scale. This is just trying to organize your information. And we want to put all of the significant points that we found. So we know we found 0, 3 minus the square root of 3 over 2. 3 halves would come next. 3 plus the square root of 3 over 2. And 3. Okay, we know that 0 is both a 0 or x-intercept and a relative min at 0, 0. We know that 3 minus square root of 3 over 2 is an inflection point. We know that 3 halves is a relative max. We know that 3 plus the square root of 3 over 2 is an inflection point. And we know that 3 is a 0 and a relative min. We know that we have in behavior that this is going up to the left and up to the right. And here's where this really gets interesting. Go back to your chart, and if you look at the intervals where this is decreasing or increasing, from negative infinity to 0, we have that it is decreasing. From 0 to 3 halves, we have that it is increasing. From 3 halves to 3, we have that it is decreasing. And from 3 to infinity, we have that it is increasing. And then when you go to kind of overlay that with the concavity that you just found, notice the concavity doesn't change at the same place. So this one's going to be concave upward. From here to here, we're going to be concave downward. And from here to here, we're going to be concave upward. Okay, so from there, I am going to put it all together. Now, I usually like to start by figuring out or graphing all of my important points. So I'm going to start by graphing the 0, 0. I'm going to graph that 3 halves 81 over, I think it was 81 over 16. So that is going to be about 1.5 and a little bit above 5. It's an approximation. It's a sketch. I'm going to graph my 3, 0. And I'm also going to graph those inflection points. So we had about 0.6 and about 2.25, so about right here. And we had 2.37, 2.25, so right about here. And we know that on the left we are concave, or on the left we're going towards positive infinity, and on the right we're going towards positive infinity. So we want to make sure our final graph does that as well. Now, this is a sketch. It doesn't have to be perfect, but you do want to show at least your intercepts, your relative extrema, your end behavior, and your concavity, and your increasing, decreasing. So when you sketch it out, it's okay if you need to kind of exaggerate the concavity a little bit on your graph just to show it. So we're starting out up in the positive infinity. We know that from that point to 0, from negative infinity to 0, we are decreasing in concave upward. So I want to show that decreasing in my graph, and I want to show the concavity. So I'm going to draw kind of a swoop in that direction. Notice it's opening up like a bowl, catching the water. And when we go from 0 to this 3 minus root 3 over 2, we are increasing in concave upward. So I'm going to continue the concavity, but I'm going to switch to increasing. So it's going to look like this. And again, you can exaggerate the concavity if you need to a little bit. We're going to change our concavity at that point, but we're still going to be increasing. So again, it's an exaggeration, so that's okay. And from here, we're going to be decreasing in concave down. Here we're going to be concave upward and decreasing still. And at this point, we're going to be concave upward and increasing. So that would be a sketch of my graph. It's kind of rough. I'm aware of that. Yours can be kind of rough too. It doesn't have to be a work of art. It just kind of has to show all of the pieces.